Great, so in this section we are focusing on the machine learning workflow. We're talking about the principles, how we get from data all the way down the other end to deployment. So I've been through this before, but just quick overcap of what we're going to cover in this explainer is realize my picture shows like this idealized view of machine learning workflow. And so we're going to look across the top basically. We're going to talk about data preparation, so how we get from raw data to sort of useful or machine learning ready data. We're then going to talk about feature representation. So that's around about like what we include in the data set, what we don't, how we include it. And that's a really important part, and I'll tell you why in a minute. And then once you've got that, kind of coupled with how you do the representation, you want to start thinking about which machine learning algorithm you're going to be using. In this section, overall, we're not focusing on individual algorithms. We're more talking about the process which you would go through with most algorithms about how you get all the way through this pipeline. So I will iterate because lots of people think, oh, machine learning, I just apply this method. Machine learning is not a single method. I think of it as a pipeline of multiple operations. You're processing data, you're looking at data in different ways. You may be compressing the input data to a particular representation because that's efficient for your problem. You're then fitting a model, validating a model, and then deploying it. So I like this idea of pipeline, and that's probably driven that in sklearn, they have something called a pipeline, scikit-learn. So a bit of a snapshot of code there. And what this shows is you can just build sequences of different algorithms. So in this little snippet of code, it's got something called a min-max scaler. So you're rescaling all your input data to 0, 1 based on the min-max values in the data set. You're then, once you've done that, you're transforming it into a polynomial space. We'll talk about that in linear models. But it's this idea that you could have a rescaling and then project it in a new input representation that make the pipeline. I really like this idea that you can sort of construct bespoke pipelines for your data. I would say that the idea at a high level, machine learning is when you have these building blocks, it's being really good at crafting these pipelines and how you build more sophisticated algorithms. Even the ones that are used in large language models now are really about how you construct those chains. You might have heard of LangChain recently, also a pipeline, but essentially how you construct these pipelines for your task. So great. So first of all, we're going to look at data preparation. It's really not that glamorous, but it's really important. So I was asking the team at digiLab, on a new project, how often, that you haven't really seen before, how long would you typically spend on data preparation? And they said to me, it's kind of like 3/5. So 60% of their time really is about getting their data in order to then try and do different things. So that shows how important it is to build good machine learning models. And what I would say is that, that 60% is when you haven't seen that kind of data before, and you need to start establishing good preparation pipelines to understand how you clean your data, how you line it up so that it fits within your algorithm's constraints, or how you tidy it up so the labels are consistent, for example. So it's really good if you're going to do the task a lot, that it's a data set that you're going to be using all the time. Don't think manual. Try and build good reusable data preparation tools. If you use Excel, those could be macros, for example, but really think about how you can repeat that process and it will speed everything up. So we're going to go through in more detail a number of things that might come up at this stage. It's not an exhaustive list, but it's ones that we look at quite a lot. So non-alignment of data, I'll go through that, but particularly true for time series data, IoT sensors, Internet of Things, kind of sensor data that gets polled at different times, really common that it's not all aligned. Missing data, I'll show you some of the things that I've had in my data sets that are either missing or labels that you wouldn't expect. Partial data, dealing with partial data is a machine learning problem in itself, or can be. Noisy data, really common. Physical systems are inherently noisy, so you've got to handle that. And then interestingly, outliers that go with that. So noise is kind of like random noise that you should be able to deal with. But sometimes you get outliers and they can be really challenging to deal with. Are they noise or something different happened here? Identifying those is really important. And then the last one I'm going to look at is called imbalanced data. I'm going to particularly look at classification problems when most of the data you get a no, and then only a few of your examples give you positive outcomes. This imbalance in data makes them quite hard to use them just as they are in terms of building a good machine learning model. And there's strategies around what you can do there about building better data sets from what you've got, which will build better machine learning models. So let's go through these. So yeah, let's go back to the first one, non-alignment of data. Really common, right? It's super common when you have time series data. So the little picture on the right-hand side shows you two data streams. And what we ultimately want is we want them all on common timestamps, so T0, T1, T2, T3. But these sensors are essentially polling at different frequencies. And so how do you get a value at T1 when neither of the data streams give you a value at that time? This can be resolved typically by interpolation. This is where we take weighted averages of points you've received either side of that point, data point that you'd like, and you generate a new data point which is an appropriate average. There are more sophisticated interpolation methods, but they're based on the same principle. So you would typically see this in time series data, but there are other examples where you would see it as well. Missing or impartial data. I've seen all sorts of things in data sets. Sometimes if there's no entry put in, it could be blank, but sometimes you could have -1, 99999, none, NaN, which stands for not a number. I've even seen gone home in a data set. So being able to deal with these so they don't cause problems when you try and put them through algorithms. For example, if your algorithm is expecting a number and it gets gone home, it really won't know what to do with it and you'll get an error. So you need a nice, precise, clean way of cleaning that data. So you either remove or you do something with those missing values. One thing you can do is sort of provide prior inputs or sensible inputs. So if there are ranges of parameters you would expect, if you expect the numbers, say the temperature, to sort of vary between 18 degrees and 23, but you end up with lots of repeat numbers at 22, all the same, then you're unlikely to get all temperatures exactly 22. They're likely to be 22.01, for example. So sometimes repeated values can highlight that there's some kind of error in doing so. Once you've got missing data, you can do two techniques. You could do interpolation as well. You could see the first problem, non-alignment, as kind of a missing data problem, or something called imputation, where you try and look for correlations in the data which allow you to fill in those values. Sometimes, actually, sort of missing or partial data is actually a fundamental machine learning challenge itself. So the one that I know well is called the Netflix Prize. I can't remember the year, maybe it was 2006. Netflix offered £1 million to someone that could solve this problem most effectively. And so I've got an example in the picture. Say there's 12 films on Netflix. I know there's many, many, many more. And you have customers, and each of the customers only watch a selection of those films, and they rank them out of 10. Now, what you want for a recommender system is you want to know over the ones that, say, customer A hasn't seen, then you'd like to give a predictive value about what they might give as a score to 5. This is a missing data problem, or could be seen as a missing data problem. And so this is a well-known problem that you can do. Once you fill in those values, you can rank the films that they haven't seen and potentially recommend other films that they would like to see. So that's how Netflix recommender systems worked. And in 2006, they set up a prize for people to tell them the perfect solution. So really good story. Noisy data. So the strap line here is don't get rid of the interesting bits. And that can be a really hard question. To smooth or not to smooth. So on the graph on the left that I've just sketched, what you see is typical data that you might see in a sensor, for example. Sensors aren't perfect, they're noisy, they could be affected by, say, temperature, for example, that makes them noisy. They could be jiggled around on a bus, if they're attached to a bus, for example, and that changes the sensor readings. So it's not atypical. It's very common, actually, that data is not perfect. That might affect, some algorithms are robust to that kind of noise, some algorithms are pretty sensitive. So you could smooth the data, which in itself is also kind of a machine learning challenge, like how do you fit the trends to the data rather than the noise term. But maybe for certain algorithms this is really important. On the right, when is an outlier an outlier? So clearly, I think, I've constructed it this way. You've got a straight line relationship, and so all the points that are black dots are clearly come from this simple relationship. But the red dots are clearly outliers away from that distribution. Either something's gone wrong in the data collection, or it's another process that you're observing, that it's a sort of a switching behavior. Now, if you think about the one in orange, then it's really difficult to say whether that's an outlier or just noise. And so these can be particularly challenging problems in data preparation. There's various modeling techniques you can use to try and identify outliers. You can also look at sensitivity, so you can fit models with data points in, you can fit model points with data points out. And if it doesn't really change the answer, then you could ask, well, it doesn't really matter if I call it an outlier or not. And so there's different techniques you can do to handle this kind of data. But important, you don't want to eliminate interesting behavior in your data. We had a really good example with water sensors once, and most of the time the data is kind of average and fairly constant. But when it rains, one of the parameters suddenly shoots up. If you use standard techniques for eliminating this kind of data, this noise in the data, you'd actually eliminate the interesting bits, which is what we wanted to look at. So you must be really careful to make sure that you're not confusing complicated behavior of a system and noise, right? So be careful. Okay, great. So one of the other challenges that you often see, particularly in classification problems, is around imbalanced data sets. So what we mean by an imbalanced data set, really common, is if you've got a data set, look at the pie chart on top right, okay? So what if the data set, most of the data says, no, this is not true, and then fundamentally there's only a few that say yes. This could be really common, like in designing of a bridge, when something goes wrong, most bridges are designed to stay up for long, long periods of time. So in your data set, you hope that most of your data comes from no, there's nothing wrong with the bridge, rather than yes, there is something wrong with the bridge. In medical scans, for example, cancer patients or people being screened for cancer, luckily they're rare conditions, and so most of, if you take general scans of people, the answer will come back, no, they don't have skin cancer or lung cancer. Unfortunately, a few will come back as yes, but it will be proportionally much, much smaller. The fact that if you're trying to then build an algorithm which classifies this yes or no, the imbalance in data set comes a real problem. I mean, for once, you need to redefine good. If you've only, on average, 5% of your data says yes, a simple algorithm that always says no will be 95% right over your data. So one, you need to redefine good, but that's a separate story. The other thing you need to do is you can rebalance that data. So you can do this by undersampling. So undersampling would be by eliminating lots of the no's so that the no and yeses are equal or closer together. I don't like this particularly because you're throwing away data, and that, as a data scientist, that feels wrong. Oversampling is a technique where you're trying to build synthetic data on what you've got. So you can try and increase the number of yeses. Smoked, synthetic, synthetic minority oversampling technique, right, got there in the end, is one technique that you can use for oversampling. I've drawn a picture of the steps. I've got an explainer online about this, but it's quite a nice little idea. What you do is you basically pick one of the minority samples, and then you look around that minority sample, and then you say, okay, where's the nearest neighbours to that? So we've been through nearest neighbours, so you should know about that. And then in that nearest neighbour, you randomly pick one of the nearest neighbours, and then you generate a new data point randomly between between these, the one you originally picked, one of its neighbours, you generate a sample along this line. This gives a new data point in the neighbourhood of data points which are from the minority, which is likely to be a yes sample. This sort of synthetic generating of data helps you rebalance your data. And we'll get into examples of this probably throughout the wider course and probably in this course as well. So I think one thing to say is, like, we've gone through some of the sort of tasks that you might be looking at when you're thinking about data preparation, and that's great. But really, if you're in a situation where you can think about how you curate and store data from the off, it's really helpful if you know you're going to be doing machine learning, or in general just any analysis of that data, that you kind of think about it in the data creation step. Sort of classic saying, start with the end in mind, start with machine learning ready data, and it will save you a lot of hassle. So one thing I always say is don't throw away data. So if you have metadata around your data, so where was this data collected? How was it collected? Who collected it, for example, then include that in your data set. Don't just have the values. Equally, don't average values. I've seen lots of data set when they said, oh, well, the data set was very big, so we just took the average value over the day. It's a nightmare for a data scientist because you've lost a lot of information. You've made a choice about how you're going to present that data. And it might be really bad for the kind of question you're asking. I think for big projects, it's really sensible to build a data management plan. Who owns it? What's the license to it? How do people access it? What's the format in which data is going to be accessed and stored? It's not exciting stuff, but really important, and really on big projects will help you in the end. If you do a search online, lots has been written about the FAIR principles of data curation. So in the top right hand corner, it's a nice picture from the Turing Way, which is sort of guidance on good curation of data. Really worth a look. But FAIR stands for findable, accessible, interoperable, and usability. And they are some core principles that you should think about when building data. I'm not going to labour the point here, but I think if you're starting out on your machine learning journey and you have the ability to make these choices rather than just inherit a data set, then it'll be really good if you can try and think about what you're going to do with that data before you start. So data representation, it's kind of, I call it the art of including what is needed, not everything. I'm going to jump forward in a minute because really I think this is a fundamental concept in machine learning. And a lot of machine learning is around this idea that you want to extract the important features from your data, then build good models, right? And why is this the case, right? So let's talk about the curse of dimensionality. It sounds like an impeding doom. It might be if you're trying to build a big model. So I always look at this. The strapline is everything is far away in high dimensions. So what do I mean by that? But let me tell you what high dimensions mean. If you think of a picture as an input, so I've talked about this before, like machine learning algorithm has a picture of cats and dogs. Machine learning algorithm would like to decide whether it's a cat or a dog for an unseen picture. A picture might be made up of 480 by 640 pixels. Each of those pixels has 3 numbers associated with it. So in total, that's like just over 900,000 numbers describe that picture. We call that the dimension of the input space, and it's extremely high. Now, if you want data to be close together, so I've drawn a straight line here, so this is a 1D, we can equally easily space points pretty close together on a line. So here we've put 3 points. If I kind of want the same spacing in 2D, I need to do 2 to the power of 3, which is 9, right? So I need a grid of 3 by 3, 9 points. If I then extend that to 100 dimensions, you can see the number of points with the same spacing I require is 5 to the power 10 to the 47, right? Eye-wateringly large amount. If I actually did the 920,000 example, I don't even dream what that number is. Huge. Okay, so but the point is that the more data, the more inputs we have. To get good coverage of our space, we need more and more data. So we can collect more and more data. We can't collect that amount of data often. And so one of the techniques that is often used is about really thinking carefully about your representation of your data, trying to reduce this dimension to a much smaller amount so that you can get away with much, much less data. And so go back to the example with identifying a cat. You don't actually need to know all the pixels in an image to understand whether something's a cat. Humans identify cats by features, pointy ears, particular sort of nose, as opposed to a dog, different shape, face, for example, a waggy tail, whatever it is. We have certain features. We don't work in pixels, is what I'm saying. We look at pixels, but then we extract features from those pixels, which then help us to decide, is it a cat or a dog? Machine learning algorithms work in the same way. I mean, they're designed to work in the same way. We thought, about how humans solve these problems. So the picture in the top right is really is what we call an autoencoder. It's a particular neural network architecture where we have a very large input and then we try and squeeze it through a bottleneck and then we reconstruct the large output. The algorithm then tries to minimize the loss of information by squeezing it through that bottleneck. This condensing of data means that to get good reconstructions or decoding of that information, we need to extract the important features. This is a whole area of unsupervised learning or dimension reduction. And in linear model section, we're going to look at principal components, which is one of those techniques used for this, a really central technique. So you don't have to just use machine learning for representation. You can sort of engineer features quite heavily yourself, and that's often what's done. I mean, there's a lot of information in an expert. So if you've got a large feature space or large input space, but someone knows a lot about the kind of data generating process which your data comes from, you could ask them, well, what do you think is important in this data? What should I look for? And that might help you reduce the data set. So it doesn't all have to be fancy machine learning. These can be engineered feature representations that help you reduce your data to the important information to do the task that you're doing. I think the other thing you should think about is around data leakage. One thing that you need to be careful of is sometimes people include information about the outputs in their input data, which means that it doesn't generalize well. So you could think of an example where I saw an example. So there's a body fat example which we've used. I think it comes in the next section actually. But a body fat example where various measurements are used to calculate, so like circumference of tummy, chest, neck, for example, and they're trying to use that to infer what the BMI, body mass index of a group of men are. And the idea being that BMI is quite complicated to measure, or body fat percentage, I think actually not BMI. Body fat percentage is quite expensive to measure, but measuring the size of your neck and your tummy is really easy. So you can get good ideas about how healthy that person is by learning the relationship. In that data set, there's something called density, which is calculated as the first step of calculating the body fat percentage. And so, if you build a model which includes in the inputs density by accident, then you would live in a situation where the model's meaningless, right? You've essentially included inputs, the outputs in your inputs. And there are other examples of this. So be careful when you think about how you construct the inputs of your models, that it's consistent, that you can actually deploy it in the wild, that you haven't kind of cheated the system. So just some thoughts. So we've been through the curse of dimensionality. So the final bit of this explainer is around model selection. There's a favourite saying that all models are wrong, some are useful. So there's no such thing as the perfect model. So I hear one model to rule them all. I could have probably a meme of Sean Bean, I'm sure, but I didn't go for that here. I would just highlight, again, machine learning is not one method or approach, and often model selection is required. You need to try different types of approaches on your data. You don't know what's the perfect, when you're dealing with data, there might be different approaches, different parameterizations of your model, that work better. And so a really important part is sort of discovery of these different models, trying different ones and seeing which are best, but also knowing what the methods that you can use are best suited to. And so things you might consider around like data type, how much data do you have? Some methods require a lot of data. Neural networks are a really good example of that. If you have not much data, using a neural network is not a good idea. What's the input type? Is it a number or is it a classification? Will influence what kind of method you will use. What's the task at hand? This is kind of an obvious thing, but are you classifying something like image? Is it a cat? Or are you regressing? What's the weather like in an hour's time? The answer that you seek, right? So what do you need? Do you really care about a prediction, which you might know? Do you need an answer? Or do you actually care about uncertainty more? And if you require uncertainty, so how much should we trust this output? And that leads to fundamentally different types of methods, right? So I would say a key take-home message for this course is to start you thinking about what each of the methods do and what the characteristics of each method, so you can make good choices about model selection early doors. So I fit like some kind of principles for me about what makes a good model. And it's kind of this ability to predict versus complexity of that model. So this is a really common thing that you do, but there's a whole area of maths, computer science, machine learning, which talks about information criteria. And this is a kind of a way of including scores about how good models is. It's generally accepted for me that a good model is as simple as it can be to be sufficiently accurate for your application. And the thing is, sufficiently accurate depends, right? If you require millimeter accuracy in a problem or meter accuracy, then that should drive what you believe is good enough, right? So I can't say a number of what's good enough, 1%, 2%. It really depends on the application. And then, so the idea with information criteria is the fact that your score, the quality of the model, has two parts. Has this lack of fit, so you want good predictions, but you also want to be penalized for model complexity. So too many parameters is not good, particularly if it doesn't lose to well-fitting models, right? The idea is you aim for the lowest score, so you want a smaller lack of fit as possible, so you want the best model as possible for the simplest complexity. Often this involves building lots of different models with different parameters, ranking them and then picking them. So the software we actually build in digiLab, it's called TwinLab, it does this for you. It has the ability to sort of fit a whole bunch of, like an ensemble of models, and then it ranks those models for you. You'll see an example on the right hand side. It might not mean much in terms of the different terms, but model A to L are different combinations of choices in a particular model that we built. And then this negative AIC is really one of these information criteria. It's on a log scale, so the negative bit represents that. So the lowest score is represents the highest, the longest bar on this graph. And what we did was we fitted A to L of the models, and then we rank them in criteria. So we can see like D's the worst, and I gave the best model information criteria. Not the best fitting model actually, but much fewer parameters in this particular model. Okay, so take home messages for this explainer. I'll keep repeating this. There's not one way to do machine learning. There's not one perfect model. You're going to have to try and build quite a few. So be open for that. Building a few models lets you see the positives and negatives on the model that you're ultimately going to deploy, see the sensitivities of it. So really good practice to build a few, allows you to compare different approaches as well. So be prepared to build lots of models and look for tools that allow you to do that easily. Sort of repeat the fact that if you haven't collected your data yet and you're collecting your data to ultimately do machine learning, really invest time in thinking about how you do that so you have a good data set. You'll reap the rewards in the long term, like actually sorting out your data, making sure it's machine learning ready, making sure you've got as much information as possible, and that it's well collated is really important step here, right? So the final bit in that, when you start having to process your data, prepare your data for machine learning, if it's a repeated process, make sure you record your kind of data pipelines to how you process your data. Not only will you sort of be able to repeat the process in the project that you're doing, but you'll often find that actually lots of these processes are very similar. So in digiLab, we have a whole library that we use on our work, which we share between the team, that they use because often on a new project, we've seen similar kinds of data processing steps before. Start building your own library or use tools like ours that let you do it efficiently. Great. See you in the next explainer.